So, in the last class, I just gave a brief introduction to folding. That is, I just told you the philosophy for folding. Folding is basically used for cheap area minimization and therefore power minimization also at the cost of throughput. In folding, what we do is this: suppose there are many nodes in a DFG which represent the same hardware function, say adder. Maybe there are 10 adders, so one adder is one node, another adder is another node like this. So, there are 10 nodes in the DFG. They are located here and there, maybe connected, maybe not connected with each other like that. Okay. But they all perform the same physical operation, that is addition. So, in folding, what we say that instead of employing 10 adders and therefore requiring so much of area and power and all that, you use only one adder. Okay. Then I say I am folding it by a factor of 10. 10 adders merged into one. As it is folded 10-fold, 10 times. But then that means how to do the job of all those 10 adders? You have to do them by a time division multiplex manner, which means you have to run a faster system clock, at least 10 times faster. So, I mean, you will just use the system clock, and this particular adder which will be using, that will do the job of those 10 previous adders in a time division multiplex manner. Now, which order to follow, whom to do, I mean first, and whom to serve second, and whom to serve third, and all that, that order is called scheduling. Main problem in folding is the scheduling, to choose appropriate schedules. Okay. So, of course, you need switches also, because you are doing this multiplexing and all that. Okay. Just to give an example, very simple example from this book. Suppose you have a thing like this, one sequence A n, this is an adder, just two adders. So, you see this circuit, not even DFG, has got, I mean, two adders, right. There is two units which do the same job, right. Now, I want to replace it, I want to fold it by factor 2, that is, instead of employing two adders, I will be employing only one adder. But I will be employing, then I will be using a system clock which is 2 times faster than the clock which is which is related to this inputs. Okay, the input clocks. Okay, that is what we will be doing is that maybe I use only one adder, and I use switches. Here I give A n, this switch comes to here at 2L, since the folding factor is 2, okay, and therefore, system clock is 2 times faster than input clock. That means, one input clock period means 2 system clock period. Okay, that is why I am taking, I am in terms of the system clock period, I am having 12 plus 0, 12 plus 1, okay. Like the Lth, let me put it this way, Lth input clock, in terms of system clock, how will how will that be represented? It will have 2 shorter clock periods. One will be 12 plus 0th, one will be 12 plus 1th. Like this for the 0th system, 0 1. Then first means 2 3, like that. Okay, 12 plus 0, 12 plus 1. Because L system clock means L input clock means 2L number of system clock. Then 0 the first guy, 1 the second guy. Okay, so 12 plus 0, this also comes at 12 plus 0. So that means I am using 2 times faster clock here, system clock. In one, and I am using, so I have to use switches. Switches are must, of course, we have to do multiplexing. Actually, there will be multiplexers. So this touches here, this touches here, these two get added, and then I need delay. You see, this delay was nowhere here earlier, but a delay has come. This also another phenomenon, another typical feature of folding, that suddenly you find that more delays are coming in the system, and therefore, after folding these hardware units and you get some kind of structure like this, I mean where many delays are coming, you can do further folding to even minimize the delays, number of delays. There is many delays can be mapped into one delay, and again using some of switches, same delay can be used in a TDM manner, by various edges and all that. Okay, that is the next step. But you see a delay is coming. and this delay is with respect to the system clock, faster clock, because this result needs to be stored. A n plus b n, whatever I have, that is stored in the next cycle. That is 12 plus 1, 12 plus 1, I give C n here. Actually, A n is valid over the entire Lth, A n, B n, C n. They are standing there over the entire Lth input clock. But this switch touches takes this and takes this, samples them only in the first half of that Lth input clock, right. That is at the 12 plus 0th system clock. Okay. And then at 12 plus 1th, it takes this data and it takes this, adds them. So, then you get a result. Okay. And in the next cycle, it comes out, and that times 12 plus 0, that time you take the output. So, here you see what is happening is this A n, this input you are giving, I mean after giving one input, after how much time you will give the second input, that is first I give A n and B n, this addition is done one cycle. If adder takes T a amount of time, T a unit of time, so one T a period gone, then the second addition, that is with this result A n plus B n, you had C n, so another T a gone. So, that means you have to wait for 2 T a unit of time. That means input clock is at least equal to input clock period is at least equal to 2 T a, but system is can be system clock can be just T a, isn't it? You see, isn't it? One clock, one system clock means one addition done, next system clock another addition done. So, essentially you see the same thing we are saying that you are compromising on throughput, that is you are using a faster clock, but you are not able to process data at the same clock period. You are constrained so that you cannot take data at that high rate, you have to take data at a lesser rate, but then you are gaining on chip area and power. Okay. This is a kind of trade off, right. Now, I will be generalizing it more now, I will be kind of devising some algorithm. This is just done in a just using our intuition and all that, very simply done, but in a very general setup in an abstract DFG how to do things. That suppose there is a DFG, there is a DFG and that has got several nodes, DFG, so you have several nodes U, U prime, U double prime, dot 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 dot. Say total how many? Say m number of nodes, where node function is same. If this is an adder, this also adder, this also adder, all them are adder. They represent different nodes in the DFG, but their actual physical operation is same. Okay. And total number is say m. Right. Again say another set of nodes V, V prime, V double prime, dot 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 dot, say L number of nodes. Their physical operation, there is same hardware unit, H, I denote it by HU, H for hardware, HU, that is hardware unit of the type U, because all the nodes they are either U or U prime or U double prime, that is U category. So, for all these U category nodes which have the same operation, say adder, instead of calling it adder I call it HU, H for hardware, same type of operation, okay, HU. Similarly, they have another HV, and you choose a factor n which is greater than equal to, or you can write max of, okay, just a factor, and I will say that I will be folding this DFG. Say to make life simple, you can even assume that DFG consists of only just two kinds of nodes, one of this kind, another of this kind, say adders and multipliers, just two kinds of nodes. This has got say 10, this has got 12, I choose n to be say 16, so I have to fold it by say factor of 16. In general, it has got m number of such nodes, it has got L number of nodes, okay. In fact, this is not required, this I will come to later. I am choosing to start with, I am choosing this, but this can be relaxed. What is this? What is important is this, we have understood this folding philosophy. So, that means instead of having say n, instead of having so many hardware units, say HU, concentrate on the U type, U category nodes. Instead of having so many hardware units of the type HU, maybe I will be using only one HU, isn't it? One HU. It will do the job of all those m number of hardware units by using a faster clock and working on a time division multiplex manner. Okay. Ordering is the scheduling, whether to start with U or U double prime, then to follow with U triple prime or U. That ordering is how to schedule them. Okay. That's what I'm coming. But essentially all the hardware units, at least n of them. Okay. Let me relax this. N, you just take n, forget this. N can be less also. Like this, suppose you have got 10 adders, there is no need that you fold by 10, you can fold by 5 also. So, 5 adders into one adder, another 5 adders into another adder. Okay. That kind just becomes a little more complicated, because you have to handle 2 hardware units for the same category. So, I just trying to avoid it, but to make sure that no incorrect message goes, let me relax this here only. Okay. This is the hardware unit. So, what is this doing? It will try to work for say U, hardware unit U once, hardware unit U prime once, U double prime. Order is scheduling, that is later, but I am just showing that there may be one line here, another line here, dot dot dot, another line here. This line means when HU takes data from this line, maybe it is trying to work for say U. When it tries, that means there will be a switch. In fact, this is not the way. Is a switch, if I see the switch, line should be this, the commutator arrangement actually, this way. This is a switch, it will move from line to line. This is a time division multiplexing move, isn't it? This could be U or U prime or U double prime, this could be U or U prime or U double prime, that ordering is secondary, that is scheduling. But it will touch once, process it, then sample the next guy, okay, then sample the next guy. If it so happens that total number of the folding factor n, it can be equal to m, it can be less than m, it can be greater than m, I relax that condition. If it is greater than m, then some dummy lines will be there. That is, there will be some cycles in this time division multiplex manner where nothing will be done. Because suppose there are 4 adders and you are using n to be say 6, there will be 6 clock units, system clock. So, 4 will be used for tapping those lines, but 2 will be just don't care kind of thing, okay, but you don't do anything, you don't tap anything. So, those will denote by phi persons, okay. What is happening? Suppose it touches this first and this hardware unit is HU. Then when it comes to this, how much time I should give, before this moves from here to here? That should be determined by the time taken by this fellow, isn't it? Until and unless this operation here, say adder business is done, I cannot pump in another data. So, that means by this TDM operation, this is limited by the time taken by this hardware unit. Like in the previous example, we had the adder, okay, we had the adder. If adder takes 2A, then I was taking 2 TA time actually, okay. Touch here like that, okay. So, this is given by this time. So, that is a constraint, that is I cannot, that means I cannot arbitrarily increase the system clock, so that input clock is reasonably high. The system clock is constrained by the fact that HU takes its own time, I cannot beat that time, I cannot pump in data at a rate, at a period shorter than the time taken here. If it takes a time say TU, then I can move from here to here at a time gap of at least TU unit of time or more, isn't it? And that gives a constraint on the input rate, isn't it? That gives a constraint on the input rate, I cannot make it faster. So, to avoid that, to compensate for that loss on that input rate, maybe you can pipeline it. You can, if it is possible to pipeline, of course, you can pipeline it, that is, you can divide into stages, you can into some latches, pipeline latches, there is delays, pipelining you all know. So, that the moment this stage is crossed, you can move from here to here. Okay, give the data here. Again, when that data crosses this stage, you move from here to here. So that way the speed goes up. Okay, you can apply a faster system clock and therefore faster input clock. So that means to compensate for that loss on the input clock speed, you can pipeline. You should look for pipelining it. So you pipeline it by some number of latches. Okay, in my model. In my model, I assume that HU pipelined by PU number of pipeline latches. Latches means delays. Why pipeline? Purpose I told you. If you pipeline it, then you really don't have to wait for data to come from here to here and then move this switch. It just crosses one stage and immediately you can move. So, input data, the loss on the input data rate, okay, that is somewhat compensated, because you can apply first, I mean you can beat the constraint of this TU unit of time coming from this. Okay. So, this speed goes up means you can move here faster, and therefore, overall input rate also can be made faster. Okay. This is PU number. Now, consider a general case that suppose you have got a set like this EU in the DFG. I told you to make life simple, you assume that there are only two kinds of nodes, U kind and V kind. U kind you have got EU, U prime, U double prime, dot dot dot. So, total M number, and V1, I mean say V prime, V double prime, dot dot dot. Say K number, K or L number, and you are folding by factor N, capital N. Folding factor is N is folding factor, that is N of the hardware units will be folded into 1, N folding factor. All the U prime, U double prime, they represent the same hardware function HU, and that HU unit is pipelined by how many latches? PU number of latches. PU is an integer, PU number of latches. Similarly, here you assume that V prime, V double prime, I am not writing it, V prime, V double prime, dot 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 dot. How many I have? I have got L. All those L nodes actually represent the same operation represented by hardware unit HV. It could be multiplied, it could be added, HV, and again that also is pipelined. Okay, so that clock is not held up for the entire time or entire operation to be over. Okay, it is also pipelined. Okay, by PV number of this thing, latches and all that. Okay, this is the situation, and within this DFG, all the nodes are U category nodes are all placed here and there. V category nodes are placed here and there. Okay, some of them may be connected to the other person, some of them may not be. It's a general network. Okay, but just consider they are a typical edge like this, U to V. It could be U to U also. Please understand, I am saying U to V, but it could be U to U with a delay. It could be U to U prime, same category, U to U double prime, or V to V, or V to V prime. Okay, just don't think that it has to be strictly one kind of operation, it has to be strictly another kind of operation. Okay, it's a general thing. U to V, and there is a delay W. This is all with respect to the slow system clock, input clock, not system clock, input clock, original input clock before folding. Okay. So, W unit of input delay, W number of delay, that delay means the clock period for the input. With respect to that, W number of delay is there, U, V. Okay. This is there. And U category nodes, how many I have? L, M, V category nodes I have got L, and now I do folding by factor N. That means all those, I mean N nodes of the type U will be executed by only one node, isn't it? Only one unit, not node anymore, unit, and that unit I call HU, and HU is pipelined. So, I call it say HU, and this is pipelined by how many latches? PU. So, instead of showing those sections, I just do, because I will be doing some timing analysis. So, I just show PU number of delays separately, no problem. Actually, those PU number of delays will be used to pipeline this operation, but I am just, because I am only interested in doing a scheduling analysis and all that, I am showing the presence of the delay separately, but actually purpose is to pipeline this operation. That motivation I made clear earlier, why you pipeline it. Okay. So, this is the situation here, and these are those lines, n of them, and here again if you do not understand, please ask. At a later stage also it can become a little tricky. So, this also P V D. Now, capital U node, this is a general unit. It will work for U also, U prime also, U double prime also, all dot dot dot. Okay, it will use n shorter system cycles to tap these various lines. So, at one particular, that means what are those, if it is Lth input clock, Lth input clock period I am talking of, that means that will correspond to what timing here? NL plus 0, NL plus 1, because factor is n. In one input clock, how many system clocks are located? N, isn't it? And L, I am considering the Lth, the 0th, first, second, L minus 1, and then Lth input clock. So, that means what is the starting point? NL plus 0, then NL plus 1. So, what are the points actually? NL plus 0, NL plus 1, NL plus 2 up to NL plus n minus 1. Those are the points. At one of those points, maybe NL plus small u, this guy will act for this node. That small u will be called the schedule for this particular node in the folded setup. Okay. That particular schedule. Choice of that small u and all, similarly here also small v will come up. Choice of that small u and small v, that is the scheduling problem. That is NL plus u, and u could be either 0 or 1 dot dot dot. This is the range of u. This at this index HU works for u, node u, not u prime, not u double prime, u. Okay. Because here I have got a H strictly from u to v in the DFG. There can be other edges from u to u prime, or u prime to v prime, or u prime to v. There are many edges. I am just considering one. Out of which u, this particular u, it is scheduled at NL plus small u. Small u could be any of these points. So, at that point of time, it will, this guy will tap this one of the lines, which actually is the input line of this. At NL plus u, if it is tapping here, that then basically it will be working for u, means this line will correspond to the input line of this. Okay. Then only it will work, it will take that appropriate data which was otherwise flowing into this. So, that data it will take and absorb into it. Okay. So, that means that NL plus u will be touching this line, which actually is a represents this data line for node u specifically in the original setup. Okay. NL plus u. Similarly, this will have, this will be working for v also, v prime also, v double prime also, dot 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 dot. So, but factor n is common for all of them. Important thing is factor, folding factor is common. You do not have one folding factor u for u category, another for v category, isn't it? So, for this also, one input clock means n number of system clock, and I am talking of the Lth. If I talk of the Lth input clock, this will correspond to what indices? Same, NL plus 0, NL plus 1, NL plus 2, dot dot, NL plus capital N minus 1. Out of those indices at any particular index, this will work for this fellow V. So, that I call NL plus small v, where small v is the schedule of capital V in the folded setup. I have to now do something here, so that original delay is mapped equivalently. This all these were with respect to input, original input clock and all that. Okay. Now, system is running at a faster clock, there is a scheduling here u and v. I will come to all that. So, how much delay should come here when this is working for u and this is working for v? How much delay with respect to the system clock, faster system clock should come up here? That is the question. Okay. So, similarly, I write down NL plus v. Please follow this, because Pari is very clumsy here actually. This kind of physical explanations and all that is very, I will not say clumsy, he is very economic with words there actually. I mean, when I first taught it, it was taking a lot of time on me also to understand what he's trying to say. I told him also. NL plus V, here HV works for V, fine. Now, let us see, you want between U for correctness of the thing, if the data that is processed at this node U at any cycle, say Lth cycle, then after that L plus 1, L plus 2, L plus 3 and L plus Wth cycle that should reach here and be processed by V originally in the correct original system, right. If it is, you take up any particular input cycle, say Lth cycle, it takes the Lth cycle data, processes it, whatever comes up, it delays it by W input cycles, so that that fellow must appear here only at L plus W, this L plus Wth input cycle and then processed here, right. That is the thing that have to maintain here. Now, Lth cycle, consider this Lth cycle, this is original time axis, say Lth cycle may be, this is Lth. So, Lth cycle has so many points dot dot dot, this is Lth cycle, how many points? N points. Lth cycle means in terms of now new system clock, it will be NL plus 0, NL plus 1, maybe this is NL plus U. At this point, this guy works for this U. Okay. Originally, Ls cycle, it was taking the data, and then how many delays? One delay, another delay, dot dot dot. It was coming, it was processed here, and result was coming out at L plus Wth cycle. Originally, so you have to maintain the correctness. Originally, this entire cycle was the data cycle. During that time, data was absorbed by you, processed, whatever output came up, that was delayed. So, and only at the L plus Wth cycle, this result reached here, isn't it? That was the thing that you gave me. I cannot violate that, I cannot deviate from that. Whatever manipulation I do and all that, that has to be maintained in my new setup. But in my new setup, I find that Ls cycle originally means so many system clock cycles, n of them, whether here or here or here or here, fine. So, let us do one thing. I have to reach somewhere here, n into L plus W plus V, this much time is V, because then only this guy will work for capital V. Okay. Now, this much is U, 0 to U minus 1. So, how many points left behind? U. Before this point, how many points in this cycle left behind? V, 0 to V minus 1. Okay. Now, let us do a counting. I have to count the number of cycle from here to here. That is the thing. That much of delay should come up. That is the thing. That much of delay in terms of the system clock should come up in this path when this is acting for E and this is acting for V. Okay. How much is that much of delay? Suppose I count this, say 0th first up to the one just before this. How many? W 0 1 dot dot dot, say up to this. This is L plus W minus 1th, L plus Wth, Lth, L plus 1, L plus 2 dot dot dot, L plus W minus 1, then L plus W. So, if I come from here to here, how many? W. So, how many system clock points? Wn. Okay. One system clock, one input clock means n system clocks. How many from, if you start from here, take the entire one, take the entire one, take the entire, go up to the one just before this, just before this. So, you have got how many input clock, how many input periods? W only, isn't it? Lth, L plus 1th, L plus 2th, dot 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 up to L plus W minus 1. So how many? W. Each one has got n small point, n system clocks periods. So how many system clock? N into W. From that I subtract out this much, which is already I am advanced because of the scheduling. Earlier I counted the entire stuff, but this much has to be subtracted out because of the scheduling thing I am already delayed here. So how much to subtract out? U, 0 to U minus 1, 0, NL plus 0, NL plus 1, NL plus 2, dot 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 up to NL, U minus 1. U points have to be subtracted out. That means n times W minus U, but here I have to reach here. So how many points have to add? V, isn't it? So plus V, NW plus V minus U, this much delay, but out of this again PU is already present here. I have taken out that much of delay. PU amount of delay is fixed for pipelining, so that also has to be subtracted out. So if I have this much of delay, and mind you, this is a switch, there will be various lines like this. This guy will tap here at what point? NL plus, NL plus V or N into L, okay. This guy will tap here at this point, NL plus V or N into L plus 1 into V, in L plus 1 plus V, N into L plus W plus V. V is the schedule, okay, and this delay is NW plus V minus U minus PU, okay. It will be having a switch here also. Please understand, this is simple digital hardware. Only when this guy and this switch will be at NL plus U, only when this guy touches this line and works for U, that data which was earlier entering U and now coming through this line, that will be processed at what cycle? NL plus UH cycle. Okay, it may not be NL plus U, this PU delay is there, plus PU. So that will be processed here. It will come out at what point of time? NL plus U plus PU, because there is a delay. At that point of time, this output will be connected to this delay line, this particular delay line. Okay, this particular. Otherwise, at some other point of time, this output will then be connected to some other delay line, because this is working for different nodes here, U prime, U double prime, various points of time. So at this point of time, it was NL plus U here, it's just delayed, NL plus U plus PU because of the PU delay. At this point of time, again this switch will close. That means this data after being processed will come out here at this point of time, then pass through this delay, and this will again close at, it always closes at Vth point. So when it closes at N into L plus W plus V, that data will come out here. Internally setup is like this. Is that clear? I mean, it's basically a digital hardware question. You just switches. Try to imagine that this guy is trying to act for so many persons. So naturally, you have to have the switches for distribution. Nothing else. You are using switches for distribution. It use a switch and touch this at a particular time. So that data flowed in. It worked for U. That was delayed by PU. So if it was NL plus U here, this data is coming out at NL plus U plus PU. So at that point of time, this delay line, which I worked out, the delay I worked out keeping U and V only in mind, that delay will come into operation, the switch will connect here, the data will flow in. Okay, because this particular delay line is meant for V category node, this node. And then again, as it passes through this switch, as it moves from various lines, it will touch this at the Vth point in every input clock. So if you are considering L plus Wth input clock, that time after delay this data will come over here, you can see L plus Wth input clock and their Vth schedule. So n into within bracket L plus W bracket close plus V, at that point when it touches this, okay, this entire thing come here, and further after further few cycle of delay, that output will come up. This output will come up here. Okay. So, this is the folded delay. That is, I now write this. This is, or we can say, folding algorithm. It is a bit abstract, but again it is intensely practical also. If you just keep that multiplexing thing in mind and all, it is not difficult. If it is given like this to you, then we say df, let me see the notation used in the book. There is a notation df u to v, f for folding, d for delay, folded delay of what? Previously there was a edge u to v with weight w, u to v with weight w, that was the edge. On that, if you apply folding, then the new delay, on new delay for this path was equal to what? We have found out n w plus v minus u minus p u. This you worked out in the previous page, that we first took n full cycle. So, n into w, subtracted out u, added v, and then further subtracted out those pipeline delays, they are already there. Okay, this will be the folded delay. You should choose the schedule v, u, etc., so that this is always greater than equal to 0. You can ask me the question that I mean, what is the big deal? I can always, this n w is there and all that, so it can always be greater than equal to 0. You choose v greater than u. You can always ask me this question. You can always choose small v to be greater than u. And further, if you have a delay w, say 1 or 2, or you are multiplying by n, this is a positive number, it will always be greater than equal to 0. It is not that easy. The problem can come in this way. If there is a loop, if there is a loop from u to v and v to u, schedule remains same. Suppose here you have got w1, here you have got w2. This edge after folding will give rise to how much delay? N w1 plus v minus u minus p u, and this will give rise to this edge, and this will give rise to n w2 plus u minus v minus p v. Suppose p u, p v are 0, say for the time being, suppose this is 0. Also w2 0. W1 cannot be 0, it just becomes a delay free loop, which is impossibility. W2 is 0, and n equal to 2 or something. Okay. So, you have got n w1 plus v minus u on one hand and u minus v on one hand, and both must be positive. Okay. It is not that you take v greater than u, okay. Already there is a factor, and then you take v greater than u, this is greater than equal to u, immediately this will become negative. Or you take u much less than v, so okay, you take u much greater than v, so this side is nicely positive, but this overall becomes negative, because it is v minus u. It is only for a loop like this, but there will be loop interconnection and all that, so there will be a problem. So, that is why, I mean, this you must make sure that the schedules that you choose, I mean, they lead to feasible edges. Okay. That is, this folded delay should be greater than equal to 0. Retiming is one way to ensure that. That I will come in the next class, but I now take one example. Okay, I now take an example, and I do not think this example can be completed. It requires, because this folding problems, you know, are very elaborate. So many switches have to be seen, so many things. It is very big problems actually. It takes half an hour to carry out one full job. I take an example. Okay, some notations, again going by the book. Suppose, I mean, I define something called folding set S. S will be nothing but it will consist of, say, A, B, C, dot dot dot, this kind of things, where A is A, B, C, they are various nodes of the same type, like U prime, U double prime, A, B, C, it could be A, C, B, it could be C, B, A, and this order is important. order is important means A in this folding, if I write the folding set like this, that it begins with A, then in every input clock period A will be the guy to be tapped first. So, its schedule will be 0, that is A will correspond to NL plus 0, B will correspond to NL plus 1, this is the order, C will correspond to NL plus 2 dot dot dot. Okay. Sometimes it can so happen that suppose you have got only two nodes A1 and A2. Suppose you have got two nodes A1 and A2 of the same type, say adder. Your DFG consists of only two adders, one is A1, A2. I want to fold, but not by a factor 2, by a factor say 3. Okay, because there may be multipliers total 3 in number. So, 3 multipliers have to be folded into 1. So, I will take the bigger of the two things. So, between 2 and 3 I will take 3. So, suppose it is folded by 3. So, that means one cycle, when it comes to these nodes, one cycle will be wasted, because I can tap for A1 once, tap for A2 once, still one more cycle is left, and that is a waste. I am nobody to tap to. That will denote by phi. Okay. So, you can have something like this, again A1, say phi A2. That means this will be at n is 3 here, this will be at 3L plus 0, 3L plus 1, 3L plus 2. This order is not important, you can start with phi also, you can end with phi also, it is not that A1 then phi then A2. Okay. So, folding set means, I mean it is a set of nodes, all of which do the same job physically and which have to be folded into one unit, okay, by the given folding factor, and the order defines the schedule. The guy who appears first, it will be the first guy, okay, that is its schedule will be 0, its schedule will be 1, its schedule will be 2 dot 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 dot. This book also goes further, given A, B, C and all that, you develop a set, and given S, how to denote A, that is how to denote that A is the guy which has the G schedule 0, or C is the guy which has the schedule 2. It says S say 2, that is his style, S2, that is C, S. Let me do one thing, let me not use this, I do not know why he puts one more parenthesis also, S by 2, S by 0 is A, S by 1 is B. Okay. So, from here on, just looking at this only, you can say that okay, it belongs to the folded set S and its schedule is 0 or its schedule is 1, like that. Okay. Now, consider one say digital filter, and we will be using folding, but this example cannot be completed today. We will be going halfway through, we will be calculating the folded edges. I will see the problem is such, no folded edge turns out to be negative. So, feasibility already satisfied, but this digital filter is slightly different from the usual digital filters we are familiar with, that direct from 1, direct from 2, slightly different. If I use the same folding there, as I will show later, their feasibility will be violated, some edges will turn out to be negative after folding. Okay. Something has been done to the original circuit to obtain this circuit, for which folding does not lead to negative edges. Okay. This I am just telling you beforehand, for the timing you do not have to consider that. You consider a circuit like this, plus these problems are nice. I give them the names instead of A, B, C, D. I call them adder 1, adder 2, adder 3, adder 4. 4 adders, 4 multiplier. This guy 5, this guy 6, this is 7, this is 8. Okay. 5, 6, 7, 8, they are multipliers, 1, 2, 3, 4 adders. See, you know this kind of digital filters, but it's slightly different in the sense which is delays are coming in a bit. I mean, it's not, you know, I mean, you normally have what? Some delays here, one delay, that's all. Okay, and they get added this way, that way, okay, and then, but here you see the delays are distributed slightly different. I mean, I don't know whether you can remember direct from 1, direct from 2 filters. In terms of delay distribution, it's slightly different from that. Okay, you can go when you go home, you can check. Now, this is given to me. These factors are given that we fold it by factor 4, because 4 adders, 4 multipliers take n equal to 4. Number one, this is the problem. Then it is given that adder takes TA 1 unit, TM 2 unit, and you use PA, that is number of pipelining latches for this pipelining the adder. You take just one latch. Okay, I told you the hardware units are to be pipelined. Okay, that is a general situation, and say PB, PM, say 2. Multiplier takes more time, so you better you employ one more pipeline latch, so that you know some further, I mean, something is saved in. Okay, so this is given to P equal to 1, P equal to 2, and I will be folding by factor 4 means all the 4 adders to be replaced by 1 adder, all the 4 multipliers to be replaced by 1 multiplier. Okay, and my Lth input clock will be what? 4L, I mean, in terms of system clock will be these 4 points, 4L plus 0, 4L plus 1, 4L plus 2, 4L plus 3. Now comes the schedule. Okay, you are telling me fine, adder 1, adder 2, adder 3, adder 4, they will be replaced by only 1 adder unit, and so the job of these 4 will be, you know, I mean, carried out in a time division multiplication manner, but in which order, what schedule? Should I start with this first, then maybe this, then maybe this, then maybe this, then maybe this, or maybe shall I start with this, then this, then this, then this, which one? Okay. Now, this book gives already a schedule, and we will see that that schedule is okay. It will not lead to any negative edge after folding. So, I follow just the schedule that is given by him. How he arrives at the schedule, that we will consider later. Okay. Actually, this is a modified version of that original direct from to digital filter. On that direct from to digital filter, if you apply folding with this given schedule, it will lead to negative edges. Okay, but then you retime that and you get this, and you apply the same schedule, you will not get negative edges. That is by that process we will show how retiming can be used, okay, to satisfy the feasibility. So, the schedule that he chooses is S1. See, I need 2 schedules, one for the adder category, 4 adders. So, this will have the adders 1, 2, 3, 4, and n also equal to 4. So, no cycle is wasted, no phi is required, isn't it? S1 he chooses to be 4, 2, 3, 1. That means adder 4 first, that is 4L plus 0, 4L plus 1, 4L plus 2, 4L plus 3. This 4 means this guy, this adder. So, its schedule will be 0, 2 means this adder, its schedule will be 1, 3 means this adder, its schedule will be 2, and its schedule will be 4, 3. Okay. I could have given the name A, B, C, D, but following this book I am giving the name by the numbers 1, 2, 3, 4. So long I was giving U, U prime, U double prime, or A, B, C and all that. In this example he uses numbers only, digits only. Okay, that is why instead of A or U only digits come, but it gives the order. Adder 4, 0th schedule, adder 2, first schedule, so and so. This for the folding set for the adder category of nodes. Similarly, because all the 4 adders will be replaced by 1 adder, and similarly I have got 4 multipliers, all the 4 multipliers to be replaced by 1 multiplier. So, again that also has a schedule, and he chooses a schedule 5, 8, 6, 7. I have got 5, 6, 7, 8. So, his schedule is 5, 8, 6, 7. So, once again 4L plus 0 here, 4L plus 1, 4L plus 2, 4L plus 3. Okay. Now, we have to do folding. We have to first, after folding we have to see whether there is any negative edge that comes or not. So, we will just find out the edges. First, you start with this. What I have to do? Say U category, if I find out edges in the original DFG, it could be an edge from U to V or U to U, that is adder to adder itself or adder to multiplier. You understand? I told you that, I mean, that is a general situation. Okay. So, here I find out all the edges in the DFG. Because after folding, what edges come up? Because after folding, I will not employ 4 adders, I will employ only one block with one adder, and I will show separately one unit of delay to as pipelining latch. Similarly, I will employ only one multiplier, okay, and separately within that I will show 2D to indicate 2 pipeline latches. That is all. Only 2 such units, no such structure, no such structure, and switches and all that for this time division multiplication business. But then edges, after all, for every U to V edge in the original DFG, what will be the corresponding edge? That is edge delay. Schedule you have given me, 4 adders merged into one adder, that adder at 4L plus 0 will work for this guy, at 4L plus 1 work for this guy, that I understand. But from this guy to this guy there is an edge. So, that edge has to be preserved in my folded DFG, is not it? So, I have to identify all the possible edges in the DFG. I will take only one, this is I have got a signal. Start with this guy. What I will do, maybe in the next class I will use this, so that it saves me drawing it again. Just look at the, I mean, instead of carrying out anything now, just physically let us look at the edges, and I end there only. If you start with guy number 1, this is one edge going here. So, adder 1 to multiplier 1. Say adder to adder, let us consider first. Adder 1 to adder 2, 1 input delay. Okay. So, U, V you can put, pipelining latches here, pipelining latches here, its schedule, its schedule, that formula we derived. Okay. So, in the folded thing, how much delay will there be between this adder and this adder? They will be same adder, but one adder output again before being fed back to its own input, how much delay? Because so that at the schedule for this or schedule for one, it really, I mean, keeping those schedules in mind, it really amounts to one input delay. Okay. That is the thing. So, that is one edge. Another adder to adder will be, do I find any here? No, adder to adder only one. Then this guy one edge, this guy one edge, 2, this guy one edge, this guy another edge. From this it is okay. Then started adder 2. Adder 2 has got no edge, is our output 1, forget it. Adder 3, 1 edge, 3 to 1, no delay. Then come to 4, 4 to 2, 1 edge, no delay. Come to 5, 5 to 3, 1 edge, no delay. Come to 6, 6 to 4 only 1 edge, no delay, 1 delay. Come to 7, 7 to 3, 1 delay, and come to 8, 8 to 4, 1 delay. So, one from here there are many edges, but from other nodes there are only 1 edges. For each node I will find out that folded delay using that expression. We have tabulated them, and then we will see none of them is 0. Using them we will draw the final hardware, where we will have only one hardware adder unit, okay, and one hardware multiplier unit, and many switches which will maintain the schedules, okay, and each edge there will carry the delay information as obtained by this formula. Okay, that I will carry, I mean, I will calculate the resulting folded edge delay. So, those delays will be present in the edges of the folded setup. Okay. So, that is all for today. Thank you very much.